Hi, I'm Andreas, Developer Experience Lead at Tweak. We recently implemented cross-compilation support in Rules Haskell, and today I'd like to share some of the things we learned in the process. I would also like to acknowledge my esteemed colleague, Facundo Dominguez, who implemented much of this work. Tweak is one of Bazel's earliest adopters, a recognized community expert, and a contributor of Bazel features and extensions. We maintain the open source rule sets, Rules Haskell, Rules Nix packages, and Rules SH. Get in touch if you need help with your Bazel migration or improving your Bazel build. Let's talk about cross-compilation. First of all, what do we mean by it? Let's start with regular compilation. Say, for example, your compiler runs on x86 Linux. It will produce code that runs on that same platform, x86 Linux. Cross-compilation means the compiler produces code that runs on a different platform, for example, ARM Linux. It could also be a different OS, perhaps iOS, or an embedded device. This is particularly useful if your target platform is not powerful enough for compilation. Bazel adds a dimension with remote execution. Say you invoke Bazel on your M1 Mac, and the compiler runs on an x86 remote executor, while the generated binary runs on ARM Linux. So there are three platforms that we need to consider. Note the generated binary in these examples could also be a Bazel test. Bazel uses the following naming convention to describe the various platforms involved. The platform that Bazel runs on is called host. The platform that the compiler runs on is called execute. And the platform that the generated binary runs on is called target. Bazel supports cross-compilation with its platforms and toolchains mechanism. I'll give you a brief overview of how it works. We'll start with platform constraints. Platform constraints tell Bazel how your platforms differ. For example, a platform constraint might describe which CPU architecture to run on. First, we define a constraint setting for the CPU architecture. Then, we define values that this setting can take, say x86 or ARM. You can find common CPU and OS constraints on GitHub at bazelbuild/platforms. Then you can define platforms that fulfill certain constraints. For example, here we define a platform that consists of a Linux OS and an ARM architecture. Platforms are typically specific to your infrastructure and often defined in your project. The constraint values attribute shown here refers to the constraint values defined earlier, for example, the ARM CPU architecture. Finally, when you define your toolchains, you can declare which constraints a given toolchain is compatible with. The exec compatible with attribute states where the compiler can run, and the target compatible with attribute states where the generated binary can run. The toolchain type declares what kind of toolchain this is, in this case, a Haskell toolchain. To use a toolchain in a rule, you declare a dependency with the toolchain's parameter and extract the toolchain out of the context object in the rule implementation using the toolchain type. Bazel will then hand you the toolchain instance that matches the current target and execute platforms. This brings us to the first few minor things we had to adjust. Most rule sets provide repository rules to provision the appropriate compiler toolchains. Rules Haskell offers a few as well. For this cross-compilation work, we use Rules Nix packages to integrate with the Nix package manager and import a Haskell cross-compiler from the haskell.nix project. This way we can reuse the work done by the Nix community and don't have to work out how to build a Haskell cross-compiler ourselves. Previously, this provisioning rule hard-coded the execute and target constraints. We had to make them configurable to support the cross-compilation use case. For now, we only implemented cross-compilation from x86 Linux to ARM, but in principle, a user could use Nix to import a Haskell compiler for arbitrary execute and target platforms. So we made the constraints fully user configurable. Under the covers, this function sets up multiple external repositories. We had previously hard-coded some of the names for these, but in the cross-compilation use case, we needed multiple instances of the toolchain, so we had to make the names configurable to avoid name clashes. I hope this gave you a good overview of Bazel's platforms and toolchains mechanism, next I'd like to talk about a very interesting challenge that we encountered during this work: toolchains depending on toolchains, specifically the Haskell toolchain depending on the C toolchain. Let's start with a brief overview of the Glasgow Haskell compiler, GHC. GHC compiles Haskell programs to native code. Haskell can link C code and vice versa thanks to a C foreign function interface. And GHC uses the C toolchain in its compilation pipeline for preprocessing, generating native code, and linking, meaning the Haskell compiler depends on a C toolchain. To support Haskell linking C and vice versa, we have designed rules Haskell such that Haskell rules and Bazel's built-in C rules can depend on each other. To be sure that the Haskell and C targets are compatible, we use Bazel's C toolchain and instruct GHC to use the tools provided by it. The question is, how should we express this dependency in Bazel? Consider the Haskell toolchain definition that I showed you before. Bazel's built-in toolchain rule defines the constraints and toolchain type. But the actual specifics of the toolchain are defined in a separate target. Here it is called toolchain impl. The toolchain attribute defines the dependency on this implementation rule. In case of rules Haskell, the toolchain implementation is provided by a dedicated Haskell toolchain rule. You might be tempted to declare the dependency on the C toolchain on this Haskell toolchain implementation rule. In fact, rules Haskell's toolchain used to depend on the C toolchain in a similar way, indirectly through a tool dependency. What's the problem with this approach? I'll illustrate with an example. Let's say we are cross-compiling a Haskell binary from x86 Linux to ARM, meaning the binary should run on ARM. The Haskell binary depends on the Haskell toolchain. The Haskell toolchain runs on x86, but it targets ARM because it needs to produce a binary that runs on ARM. In other words, the target constraint needs to match where the thing that is produced should run. So far, so good. Now let's look at the C toolchain. The C toolchain runs x86, but it's depended upon by something that should also run x86. So it's resolved to target x86. We told Bazel that we need a C toolchain to make a Haskell toolchain, and the Haskell toolchain will run on the execute platform, x86, not the target platform, ARM. So Bazel sets the target constraint of the C toolchain to match the execute platform x86, not the target platform, ARM. In the cross-compilation use case, this provides the wrong C toolchain. How do we fix this? We make sure that it is the Haskell binary that depends on both the Haskell and the C toolchain. In code that looks like this, the Haskell binary rule depends on both toolchains. We then implement our rules such that it passes the C toolchain to the Haskell build actions as needed. The same kind of issue lurks with build tool dependencies. For example, the rule to build a third-party Haskell Cabal package depends on the Cabal wrapper, a wrapper script for the Haskell package manager, Cabal, which we use to build the Cabal package. Since it is a build tool, we declare that we need it in the execute configuration. But if the Cabal wrapper itself depends on the Haskell toolchain, then we will obtain a Haskell toolchain that targets the execute platform x86 instead of the target platform ARM, meaning cross-compilation would not work correctly with this setup. The solution is again to let the Haskell Cabal binary rule depend on the toolchain. The Cabal rules are an interesting case. It turns out that we actually need both types of toolchain dependencies. We need the cross toolchain to compile the Haskell Cabal package correctly, but we also need the native toolchain to interpret the package's build script, which is itself written in Haskell. We achieve this by adding another tool dependency to the Cabal rules that picks up the Haskell script interpreter run GHC from the native toolchain. In summary, if the rule depends on the toolchain, you will get the cross toolchain. If the toolchain or a build tool depends on the toolchain, then you will get the native toolchain. Another important subject in Bazel in general, but with cross-compilation in particular, are external dependencies. For example, packages from the Haskell Community Package Index but also things like system libraries. In Bazel, we use repository rules to define external dependencies. For example, we use HTTP archive to simply download sources or other artifacts from the web, or we use rules like maven install from rules JVM external or stack snapshot from rules Haskell to integrate with a package manager. In case of maven, we can download pre-built jars from the web, but in case of Haskell, the package index offers packages by source, and we need to download and then compile them ourselves. We need to be cautious about when we compile these packages. Importantly, Bazel's platforms and toolchains are not available in repository rules, as they are only resolved at a later stage, meaning the correct cross-compilation toolchain cannot be provided by Bazel in a repository rule. Repository rules are not hermetic, they are not sandboxed by Bazel. If we compile code in repository rule, for example by invoking the language's package manager, then it may use a toolchain that is incompatible with our Bazel project. All in all, it is best to avoid building any code in repository rules. Note, this is also a problem for interpreted languages if the package manager builds bindings to native code. Rules Haskell provides stack snapshot, a repository rule to depend on third-party Haskell packages from the community package index. It uses the Haskell package manager called stack to import packages from a curated set of compatible versions of packages called snapshots. The user defines which snapshot they want to import packages from using the snapshot attribute, and which packages they want to import using the packages attribute. So how do we avoid compiling Haskell packages in repository rule? Remember, that would be inhermetic and would not work for cross-compilation. Internally, stack snapshot is split into separate stages. The repository rule invokes the stack package manager to perform version and transitive dependency resolution, and we parse the dependency graph and package metadata emitted by the package manager. We can also read from a log file to avoid calling the package manager repeatedly. We then fetch the package sources in the repository rule using Bazel's starlark API. This allows us to benefit from Bazel's repository cache. Finally, we generate regular Bazel rules to build the third-party packages as regular Bazel targets, meaning the Haskell targets are not compiled in the repository rule, instead they are compiled in regular Bazel rules. We use the Haskell cabal rules that I showed you before to build these third-party packages. For example, the zlib package shown here. System library dependencies form an additional challenge. In interpreted languages, they're often called native dependencies. As most package managers, the Haskell package manager will not provide these system libraries for you. You can declare the dependency, and it will check for the presence of the library, but it will not install it or build it for you in a controlled environment. Instead, it will assume that the library is already installed somewhere and will just link against it. How can we ensure that we use the correct version of a system library? It is important to track these dependencies in Bazel for a hermetic build in general, but in particular for a cross-compilation project. For example, we have imported the Haskell package zlib using stack snapshot. This Haskell package depends on the C system library with the same name, zlib. We may need to compile the Haskell package zlib in both the cross-compiled and the native version. We need to be sure that it is passed the correct version of the C system library in both cases. So we need to track this dependency in Bazel. Stack snapshot lets you declare such extra dependencies for each package that you import. For example, here we declare that the Haskell package zlib depends on the Bazel target czlib. Importantly, this is a regular dependency on a regular Bazel target. This extra dependency is added to the deps attribute of the generated Haskell cabal library target. The platforms and toolchains mechanism, or other configuration mechanisms, applies with any other target. If we cross-compile the Haskell package to ARM, Bazel will give us a matching cross-compiled czlib. If we compile natively, it will give us a native czlib. Does this mean we need to build everything in Bazel, including common system libraries? If you can, this may be beneficial. But defining Bazel build definitions for all these dependencies can be hard and time-consuming, especially if you need to support cross-compilation. Alternatively, you could check and pre-build binaries or import libraries from your system's package manager. In this case, you'll want to be careful to provide versions for the different target platforms that are compatible with the toolchains used in your Bazel build. We use rules Nix packages to import such system libraries from the Nix package manager. The Nix packages project provides build definitions for many system libraries and tools, and it supports cross-compilation as well. Nix builds are also cached and tightly sandboxed, and in line with the objective to be fast and correct. We use the Nix packages package repository rule provided by rules Nix packages to import two different versions of the zlib library, one for x86 and one cross-compiled for ARM. These libraries will be built by the Nix package manager and then imported into Bazel using rules Nix packages. We can then use Bazel's select mechanism to expose the appropriate version for the current target platform under one alias, meaning when you depend on this czlib target and build for x86, then you will receive the x86 version of the library. If you build for ARM, then the ARM version. Finally, we also import the C and Haskell toolchains for x86 and ARM from Nix packages. Shown here is the import of the C toolchains. We also import the Haskell toolchains from Nix. This way, we can be sure that system library dependencies and Bazel targets are consistently built with the same toolchains. That covers all that I wanted to share today. In conclusion, use Bazel's Platforms and Toolchains feature to make use of its built-in cross-compilation support. Consider carefully where you depend on a toolchain and how this interacts with target and execute constraints. Avoid building code and repository rules, or import external dependencies using rules Nix packages in a hermetic and cross-compilation compatible way. A working example of cross-compilation for Haskell is available in the rules Haskell repository under examples/ARM. And the user guide at haskell.build includes a section on cross-compilation. Thank you for your attention. I hope this helps you with your cross-compilation endeavors in Bazel.